Hi, and welcome to this series of videos actually on second order system responses. These will be step responses. So the goals of this set of presentations will be to understand second order systems, what they are, then compare and contrast them to first order systems, which we've talked about already, or actually, I don't know whether I have a video on that or not yet, but I shall produce one if I don't. Then we need to understand the differences. There's actually three types of second order systems: an overdamped system, a critically damped system, and an underdamped system. So we'll see what those things are. There are, for a underdamped second order system, its step response, there's three performance characteristics that we should look at. Overshoot, and then the damp frequency versus the natural frequency, and then the gain. We need to understand what zeros and poles are, so we will look at that. What the characteristic equation of the system is, that will be important later on. And then there's actually a sort of shorthand way to look at second order systems. If you look at the location of their poles on the complex plane, and we will see how the location of those poles on the complex plane influences the step response of the system. And then at the end, we will actually learn how to model some second order systems in the modeling program Modelica. So let's start with I'm in chapter 4 of my textbook on control systems engineering, a practical approach. And this is the part that talks about second order systems. The part before this talks about first order systems, okay? And so this part here will cover second order systems, which are different than first order systems. Actually, it doesn't hurt to go back and look at the transfer function for a first order system. Which is what this is here. And actually what you'll see, there's some things that are useful to point out here. There are two parameters that characterize the response of a first order system. I guess before I get into that, I should describe why this is a first order system. The order of the system depends upon the highest order of s in the denominator. And here we have s to the 1, so this is a first order system. A first order system has two characteristics of that system, performance characteristics, I would say, that define the way that system is going to respond. We have a gain, k, and this is also sometimes called the steady state gain. And then we have a time constant, t. So the k governs when you put a step in. A step is a sudden change in the input into the system. The system responds, it jumps up to a new level from where it had been before. And that jump, the size of that jump, depends upon this value, k here. In fact, k is called the gain. So a lot of times you put in a unit step input. So the input goes from 0 to 1, and k is how much the output of the first order system will jump. So if you put in a unit step which goes from 0 to 1, and then the first order responds by going from 0 to 2, the steady state gain of that first order system is 2. And then the time constant governs how long it will take the system to reach its new value. A slow system will have a large t, which is the time constant, and a quick system will have a small t, because what t is it's the time that it takes it to respond. Anyway, that's all topic. That all belongs to the characteristics of a first order system, and our aim here is to talk about second order systems. First order systems have two characteristics, or two parameters, that describe how they're going to behave when you upset them, when you put an input into them that will cause them, that will excite them. So two parameters for a first order. A second order system actually has three parameters that are important. And here they are. K, which is that gain. It's the same. It has every system, no matter what order it has, will have a K parameter, a gain parameter, which says how much it's going to move depending upon, how much it's going to move relative to the amount of the size of the input that's put into it. Omega n, which is the natural frequency of the system, if it oscillates, and then zeta, which is the damping ratio of the system. We'll talk about all of these, but these the important point is that a second order system has three performance parameters that govern it. First order system only has two. Now we'll talk about these as we're going along. Zeta is a ratio of damping factors, I guess you would say. If you don't have any damping, that means that zeta is equal to 0. Okay? And zeta generally will vary, it'll vary between 0, which is no damping, and 100%, which is critical damping, as we call it. So zeta is between 0 and 1. Or no, sorry. If zeta is between 0 and 1, the system actually oscillates. Now, oscillation is something that a second order system can do that a first order system cannot do. Anyway, we'll cover all of this as we get further along. The important point here is that first order system has two performance parameters that define it, K and T. A second order system has three performance parameters that define it, K, omega n, and zeta. Now, like I said, a second order system can oscillate. It might not oscillate, but it can. A first order system cannot oscillate. End of story. And again, if zeta is between 0 and 1, then you have what's called an underdamped second order system. And the response of an underdamped second order system to a step input is a wiggle like this, an oscillation. If you have damping, the oscillations will die out. If you don't have damping, then the system will rise and start oscillating, but the oscillations do not die off. We're going to cover all of this. Now, the oscillations that are shown here, there's several features that are shown here that are important to discuss. We'll go from one value, which was 0 here before we put our step input in. This is a step response. So we put our step response in at 0, and that caused the system to wiggle, but the oscillations died out, which indicates that you do have damping, though the system ended up at a different level than it started at. And this distance right here depends upon the K. It depends actually upon the size of the input and the K. If we put in a unit step input, which goes from 0 to 1, and our system jumps from 0 to 3, that means that the K for this system is 3. But that is only if you have a unit step input. For instance, if I had a step input that was 3 and the system went up by 3, then that means that the gain of the system is 1. So what this value is right here is actually not the size of the gain. It's the size of the gain divided by the size of the step. So if we have a unit step, of course that size is 1, and 3 divided by 1 would be 3. So we could then say that our gain of our system was 3. But you do need to know the size of the step before you can determine the gain of the system. The other two parameters, omega n and zeta, we'll talk about them now, or start talking about them now. Omega n is actually not the frequency of vibration of this system. This system is damped, and therefore what we see here is what's called a damped frequency. That's what's displayed. That's the frequency at which the system oscillates. And there's a relationship between the damped frequency and the natural frequency, and it's related through zeta. So here's your relationship between your damped frequency and your natural frequency. Remember, your system only oscillates if zeta is between 0 and 1. So as you can see, this number right here is going to be less than 1. And therefore, the damped frequency is going to be less than the natural frequency. And what that means is that it will oscillate slower. A damped system will oscillate slower than it would if you added damping to it. Zeta is a measure of how much damping you have. So the greater zeta is, the more damping you have. And of course, the more damping you have, the greater the difference between omega D and omega N. So I'm going to stop right here and start a new video up to continue with this.